Sorry for the technical difficulties. Thanks for joining the DAT303 closer look at Amazon RDS for Microsoft SQL Server session. My name is Sergey Sokolenko. I'm a product manager at AWS. And we have Ellen Parsons from Viddy, who's going to join on stage to talk about Viddy's use of RDS SQL Server. Over the next hour, we're going to spend time on looking at best practices for security, performance, data migration, and data durability. A recent Forrester report identified those four tasks as one of the most important time sinks or tasks with developers, application developers, and database developers spend their time on. So we're going to be talking about best practices to accomplish these tasks. I am extremely happy to have Ellen Parsons from Viddy joining me in just a few minutes to talk about Viddy's use of Amazon RDS. Let's start with security best practices. We're going to start with a sample where you have a database and an application that accesses the database. And the major recommendation to you here is to control access to the database, starting with creating a user, application-related user that doesn't have permissions to do any DDL statements and is only focused on writing and reading to the database. So use database access mechanisms to limit access to your database through defining the separate user. The next layer of protection that Amazon RDS offers to you is a network layer protection. You can define security groups, and these security groups will allow you to define inbound and outbound rules. You can set which hosts can access your database, etc. Yet another layer of protection available through Amazon is the virtual private cloud, VPCs. VPCs are logically independent chunks of sections of Amazon Web Services. You can divide the VPC into subnets. You can have a private subnet where you will run your database and application servers. And you can have a public subnet where you will deploy your web servers. Only machines in the public subnet can access your private subnet. This way you prevent internet access to your secure data in the database servers. Last but not least, you should consider using identity and access management functionality offered through Amazon for defining and managing permissions for individual users. The next recommendation I would like to share with you is encrypting your data. You can do encryption for data in transit when it travels between your database server and your application server. It's very easy to do. To do that, you enable SSL, which is the encryption technology that supports the in-transit protection of your data, by downloading the public certificate for RDS and using the Microsoft Management Console for importing the certificate into your application server OS. The last step for using SSL is to enable the encryption in your connection string. In addition to protecting data in transit, you can also use transparent data encryption to protect your data at rest. This is a feature that we just recently launched. Many of you will probably not be familiar with it, so I'll spend a little bit of time talking about it. TDE is a native technology supported by Microsoft, and we recently enabled it in our Enterprise Edition RDS for SQL Server. It encrypts data before it's written to disk, and it decrypts data when it's being read from disk to memory. TDE is available for Enterprise Edition databases. It's available for both SQL Server 2008 and SQL Server 2012. What you do to enable TDE is adding an option to an option group and enabling that option group for your SQL Server database. Option groups are new for SQL Server with the addition of TDE. So I'm going to show you how to do it in the RDS management console. What you see right now on the screen is the option groups list in my account. It doesn't have any custom options, just the default ones. So I'm going to go and click on the Create Group button, which leads me to the option group screen, where I need to enter the edition of the database, or the engine of the that I would like to select. As I said, TD is only available for Enterprise Edition, so select SQL Server EE. And then I also need to select my major engine version. You can select 11.0 for SQL Server 2012 and 10.5 for SQL Server 2008. Once I created my option group, I can easily add the TDE option, apply it immediately, and be done with it. Well, not yet. After creating the option group, the next simple step is to enable TDE in the instance I would like to encrypt. I can either use an existing instance, or I can create a new instance, a new SQL Server instance, and use the option group during the launch wizard. In my particular case, I'm going to encrypt an existing instance called SSO10. The only task here is to change the option group from the default one to the custom one that I just created. At this point, RDS will deploy a public certificate into my instance that will contain the master instance key. The interesting part about TDE is that there are a couple of keys that are used for protecting your data. At the most basic level, you have the database encryption key. The database encryption key is the key that you use to encrypt your user database. Now, for protecting the key, the database encryption key, SQL Server uses another key called the master instance key. This key, the whole purpose of the master instance key is just to encrypt the database encryption keys. So up to this point, what I've done is I enabled the option, the TDE option for SQL Server. RDS has pushed out the certificate that contains the master encryption key into my instance. I can now go to SSMS and run a couple of SQL statements that will enable encryption in my database. The first statement is looking for the certificate that was just added by RDS. The string pattern that you need to look for is RDS TDE certificate. So I'll find this the string, and I'll save it and reuse it in my next statements. I will create the database encryption key using the previously found certificate, and I will turn on database encryption. The last couple of statements really just check that encryption has taken hold and my databases are encrypted. The first select chooses or searches for databases where the is encrypted flag is set to 1. And as you see at the bottom, the database that I wanted to encrypt is indeed one of such databases. The second select is just confirming all the databases that have the database encryption key provisioned to them. And again, the output shows I have two databases with database encryption keys. The first one is TempDB, and the other one is my user database that I wanted to encrypt. As easy as that. Let's look at performance best practices. When we typically talk about performance, we think about two goals that we want to optimize for. The first goal is increasing throughput. Throughput typically is measured by read or write operations per second, and it's a measure of how fast my database can read or write to disk. The other operation, or the other goal that we would like to optimize for, is decreasing latency. Latency is measured in milliseconds and shows, typically tells me how fast can I read from the database, individual records, and how fast can I write to the database. The three techniques that I have on the slide will help you with increasing throughput. The first one is push-button scaling. The second one is database shards. And the third one is provisioned IOPS. Provisioned IOPS will also help you with decreasing latency. Let's look at it in detail over the next couple of minutes. Push-button scaling is a simple technique to scale your database vertically. You can start with very small instances at the beginning of your usage of RDS, maybe with a M1 small that only has one virtual core and 1.7 gigs. And once you realize that the demand for your database is growing, you can scale that instance to M2 4x large box, which is a 8-core instance with 64 gigabytes of RAM. Another way to scale is to scale horizontally. You accomplish that by dividing your database into smaller chunks. And these chunks are called shards. The way you divide your database into shards is by selecting a key, perhaps the customer ID, and then deciding that all data related to customer ID starting with a 0 would go to the 0 shard. All records related to customer ID starting with a 1 will go to the first shard, and so on. Potentially, you can have hundreds of shards. You have customers who have hundreds of shards deployed, and you can scale your instances to dozens of terabytes. Provisioned IOPS give you the ability to reserve input-output operations that cannot be used by anyone else who's running on the same physical machine as your RDS instance. We support instances up to 1 terabyte in size, RDS SQL Server does, and RDS SQL Server also supports up to 10,000 provisioned IOPS. One IO operation is 8 kilobyte in the SQL Server world, so when you provision 10,000 IOPS, you're getting 80 megabyte of read and write performance. Let's say you purchase 3,000 provisioned IOPS, and you're still not getting the performance you thought you would get. There are a couple of things you should look at. First, look whether you're using provisioned IOPS optimized instances. Not every instance type where RDS is running is optimized for high I/O. You should probably start with M1 large and larger. Those instance classes are optimized for provisioned IOPS. Then you should check if you have any contention on the database level. Perhaps check if you have database locking. If you still don't see the maximum of the I/O operations that you purchased, you probably have an issue with scaling and concurrency on the application layer. And the graph on the right of the slide kind of shows a benchmarking attempt where I started with just one application server. That's the box, that's the red box. So one application server reading from my database. It only consumes about 600, 700 I/O operations per second. Now I scaled it out to 4 application servers reading from my database. And the good news is I immediately saw a 3.5x, 4x increase in read I/O for my database. By the way, I'm using CloudWatch to monitor the performance of my system. This is something that we recommend you also doing. I still haven't reached the 3,000 provisioned IOPS though. So my 4-thread benchmark test is only consuming about 2,300 I/O operations per second. So I increased the number of my application servers threads to 16. And I finally was able to exhaust the 3,000 provisioned IOPS I purchased for my database. So what this graph tells me is that actually I don't have a problem on the application scaling level. My applications are able to use all the database I/O function capacity that I can throw at it. If I have the the time to continue with the test, I would probably increase the provisioned IOPS and just see where the limit would be. So we looked at security best practices. We also looked at optimizing your SQL Server instances for high performance. Not everyone in the room has the luxury of starting from scratch and building a application in a greenfield environment in RDS. Many of us have to move data into RDS to actually operate an application. So let's look at how to move your data into RDS. You have several techniques to accomplish this data migration. You can start with bulk migration, either by using the import-export wizard if you have small databases, or using bulk copy. And you can also accomplish migration of data through replication and switchover. I'm going to give you a couple of examples of how to accomplish each of these tasks. But let me quickly comment on the individual boxes here. The choice of the migration technique will depend on the size of the database and whether you can put your database offline for the duration of the migration. The import-export wizard works great for smaller databases. It will allow you to move both the schema of your database and the data simultaneously to your target system in RDS. BCP will work with medium-sized databases, large-sized databases. The only downside of BCP is that you need to shut down your on-premise database for the duration of the migration. The last recommendation, the replication with switchover, works in such a way that you keep your on-premise database and your RDS database operating simultaneously while the data is being onboarded from the source to the target. And once the target database is completely synced with the source database, you switch over your application servers to use the RDS instance. I'll start with the example of the one-time bulk load migration. We have an application running together with a database on-premise. And what I want to do is I want to move all this data into RDS and switch my application to RDS. So I'll create a RDS instance. I will shut off the access to my on-premise instance from the application servers. I will organize an export of data into text files, flat files, using BCP. I'll use BCP as well to import the data into RDS. And then I will switch the application to RDS. I've got a couple of code snippets that will allow you to simplify this move. The first recommendation is to use the publish script wizard available in the SQL Server Management Studio to generate the schema of your database. There are a couple of optimization recommendations here. Just export the table definitions. Don't include the constraints and foreign keys so that your BCP loads can achieve the maximum performance. The next snippet is a simple select statement that will generate you the batch script that will contain all the BCP out statements that you will need to export your data. Yet another script will create a batch script for importing data using BCP in. And if you would like more info on this particular technique, you could also look up our data import guide available at the AWS documentation site. Let's also look at the second technique that I mentioned, the replication with switchover. I'm starting again with an application pointing to an on-premise database. And my task is to move all this data from on-premise to RDS. So I'll set up a RDS instance, and I'll set up a linked server in my source database that will point to the target system. I can set up SQL scripts and automate them using SQL agent. Or I can use SSIS, create a bunch of TTSX packages, which will contain insert statements that will move my data from the source to the target. And once all my data is synced up, it might take a day or two, whatever the duration is, to move all your data from on-premise, you'll switch the application to use the RDS instance. I'll give you a couple of useful statements to accomplish the creation of the linked servers and establishing this data move. The first set of statements here is to be run on the target instance, the one in Amazon. You'll create a login used just for replication, and then you'll create a user in your source database, and you will define, in your target database, and you will define, you will add permissions for this user to read and write to your target DB. In my example here, I'm assuming that I need to move a table called customers, and that table only contains two columns, customer ID and the update date. So I'll create a staging table in my target database where I will be moving the chunks of data used at each of the iterations of the replication. On my source instance, first I'll create a linked server and take note of the syntax for defining this linked server that points to RDS. We'll say something like target inst Amazon AWS.com and then the port that you chose. I will then add the login, both the source login and the remote login, to the linked server object, kind of bind everything together. And once I accomplish that, I can start writing my insert statements that target the table in my target database using a 4-part specifier. The first part will be the name of the linked server in my source database. Then I'll have the database, the schema, and the name of the table. So this simple script will allow you to create linked servers and allow you to do ongoing replication with a switchover. Last but not least, I wanted to take a few minutes to discuss or talk about data durability. The biggest suggestion I can make to you is using the automated backups that Amazon RDS provides to you. We create nightly backups and keep transaction logs for the duration during the day. This approach allows you to restore, use point-in-time recovery pretty much to any point in time during the retention period, which can be up to 35 days. In addition to automatic backups, you can also create manual snapshots. A recent feature that we just launched a couple of days ago is the ability to copy snapshots from one region to another. As you can imagine, this technique can be used for increasing the durability of your system against events in the entire region. So I'm going to show you how to use cross-region replication or cross-region snapshot copy to react to unavailability events in the entire data center. So I'll start with region 1 and a database deployed to region 1. You can use CLI, command line interface, to establish programmatic automated copying of snapshots from region 1 to region 2. And you're going to keep doing it until one day there might be an unavailability event in the first region, at which point you can spin up a new instance in region 2 and use the snapshots that you diligently copied to restore into that new instance. Hopefully, I was able to share some useful recommendations with you. I would like to invite Alan Parsons from Viddy to talk about Viddy's use of RDS SQL Server.
41 million users have shared over 6 million pieces of content from their mobile devices with us. Sorry. You guys hear me better? All right. So those users, those 41 million users have shared over 6 million 30-second videos with us. We transcode a number of renditions, and we deliver the optimal video based on that mobile device. We detect networks, so 3G gets different renditions, and the LTE networks or Wi-Fi networks will get an HD quality video. And our CDN footprint is fairly impressive and fairly large. We have over 30 million transcoded videos, and of those, we capture images, we resize images, rescale images. So we have over 2 billion image assets under management on S3. And then to give you an idea about how Amazon helps us scale, the human power of Viddy. So we have 4 executives and support staff, people that manage the community, finance, executives, et cetera. We have 6 software developers, and then there's me, the only technical operations guy at Viddy. Most impressive is that we have 0 DBAs managing all of our shards and all of our databases. So we all are acting as part-time DBAs. A lot of our community managers and interns and business analysts are able to get content that they need out of the database themselves. And RDS really helps us scale that way. This is just a high-level overview of a small portion of our infrastructure. At the top, we chose a VPC, so all of our infrastructure sits within a VPC. The top layer is a public subnet, so all of our web servers are publicly addressable stuff, sits in the public subnet. And then we have subnets for caching, so Redis has its own subnet, Memcache has its own subnet, and then RDS as well has its own private subnet. And within that RDS subnet, we have the green database is kind of the core data, stores all the users, all the metadata for videos, et cetera. And then we have 8 different shards. So we shard based on a user ID, and they go into one of 8 buckets. Each one of those 8 storage shard instances have 64 consumer shards and 64 producer shards. We'll get a little bit more into that later, and we'll break this out so you get a little bit better picture of what we're doing. So what powers Viddy? What's our stack? We're technology agnostic. The team is multi-versed in a wide range of technologies, so we choose the right technology to get the job done. Our front-end presentation layer, or API servers and our web servers, are using Windows and IIS. The first iteration was written using C# with an MVC framework. We are moving to Python, but our caching tier right now is done in Linux via Couchbase using Memcache buckets. For persistent cache, we use Redis. We have a couple clusters of Redis servers. Source control, we use TFS, and we have completely automated all builds, so we've empowered developers single-click deploys to any environment of their choice right through TFS. And for that, we use Jenkins, PowerShell, which basically wraps MS Build to deploy out to our environments. And just some of the services that we are using from Amazon, we use exclusively VPCs. We choose 1 VPC per environment, so dev, production, and QA each have their own VPC. RDS, we have 11 server instances housing over 144 databases per VPC. So in total, across all of our VPCs, we have approximately 300 databases and over 30 server instances. We use simple notification services and queuing services to guarantee eventual consistency. We use Route 53 and Elastic Load Balancers, CloudWatch for monitoring and alerting, Cloud Search we use heavily for when users search for media or search for users or search for tags. And then we also use S3 and CloudFront. We just moved off of a prior CDN, pushed over 2 billion objects into S3, and as of last week are serving content exclusively through CloudFront. Some of the early technical challenges. A lot of us at Viddy inherited the infrastructure. They built a prototype and then secured some funding, hired some devs. So we inherited a platform as a service type of architecture, which made it very, very difficult to scale. We had some difficulties in caching. We have a Twitter-based model, so if a user uploads a piece of content, they want to see that feedback immediately. If a user likes a video or comments on a video, we have to ensure that that user's device displays that instantaneously, which provides some challenges in caching. We kind of underestimated the power of Facebook. We were an early adopter of the Facebook Open Graph. For those of you unfamiliar, Facebook Open Graph allowed application developers to capture email addresses, and then a user would agree to share that content back to their Facebook feed. So if you have John Doe that's watching a video of a dog skateboarding. He has agreed to share the content back to his activity feed. We share that John Doe watched his dog riding a skateboard. All of his friends see that. All his friends click on that. All of his friends register with the Viddy service. So it creates this really instantaneous viral loop. Totally underestimated the power of it. We saw anywhere between 500,000 to 1 million new user registrations within 24-hour periods for up to like 30 to 45 days straight until Facebook kind of tweaked that product. So all those user registrations led to a very, very, very busy SQL instance. We had one SQL instance housing 6 databases. We split based on functionality. We split based on comments. We had a likes database, we had a user database, et cetera. But we saw tremendous write latency. We saw table locking. We saw delays in getting users into those tables. So what we ended up doing was completely disabling key constraints. We were lucky. Early on, we chose a global unique identifier as the primary key. So disabling key constraints really was not that big of an issue, we thought at the time. The other thing that was difficult was we are operating on a platform as a service with a very, very busy database. We were unable to get transactionally consistent database backups out of our database. So if if a developer ran an update statement without a where clause, we're screwed. So everyone was very, very careful, and it's one of the things that drove us to move off of the platform as a service. There was no way whatsoever for us to get a transactionally consistent database out. And then we also had an inflexible platform. So adding more servers would create more database load, and then on platform as a service, we couldn't just throw more money at it. So we were in a multi-tenant environment. We couldn't say, hey, here's a ton of money. We want our own dedicated hardware. It wasn't going to happen. So it provided huge, huge technical challenges. So in probably mid-2012, we started planning and made a decision to move off of our prior provider and into Amazon, with the goal that we were going to do this was absolutely zero downtime. We were still going to take and serve production traffic, and we could not afford any type of downtime during that move. So we chose VPCs, which guaranteed node affinity. It guaranteed our web servers, our cache servers, and our database servers were clustered together, and our cache servers or data was not publicly accessible. For SQL, we chose RDS, but in that process, we had a tremendous amount of cleanup. We had duplicate email addresses. We had to merge records. When users signed in, they might get record A, and then they come back later, they get their record B. So we had a tremendous, tremendous cleanup effort. And what we ended up was 144 RDS shelves, and we filled the initial load via an ETL process. And then what we did during the process was also engineer for eventual consistency. And I'll get into that a little bit later. And then the other thing that was important from the get-go was enabling developers single-click deploys to either the platform as a service infrastructure or the new infrastructure as a service. And so we built deploy scripts. Developers could build to any environment, test on any environment, ensure that their data was correct, et cetera. And then during that move, we moved all of our DNS records over to Amazon, lowered the TTLs in preparation for that move. Christmas Eve 2012, we all took a couple hours, signed online. We shut down the production instance, waited for that eventual consistency, those eventual consistency queues to go to zero, and then we swung traffic via a DNS update. So the only downtime that we did incur was approximately 1 minute to move those DNS records over. Couldn't have went smoother, tremendous engineering effort, and it shows that huge planning really, really does pay off. So how do we shard? We shard based on a GUID. So when a user comes into our service, we hash that user ID, and they end up in one of 64 different shards. So we have a total of 128 shards. A user belongs to one of 64 producer shards or one of 64 consumer shards. So our users produce content and they also consume content. So when they comment, we push to a producer shard. If someone comments on a video, they'll pull from the consumer shard. So what happens is the application servers for eventual consistency push a message to an SNS topic. And those SNS topics, we have simple queuing services. We have one queue per shard that is subscribed to those topics and pushes that message into one of the appropriate shards via a Windows service that we have running that's just constantly polling all those queues. Some of the advantages, we can lose that Windows box or that partition manager that's monitoring those queues, and we don't lose messages. There'll be a delay in delivery, but we do not lose those messages. We can lose a DB shard. So shard 01 can go offline. those messages will continue to queue, and when shard 01 comes back online, we'll push those messages into that particular shard. And it's really easy to scale. If we need to scale up in terms of shards or databases, we'll just create more queues. More queues equals more messages equals more Windows machines to process those, and we can horizontally scale. So it's very, very easy to scale horizontally using that eventual consistency type of model. So how do we provision on RDS? Not a lot of science behind it. We didn't have a ton of visibility at our prior provider. Didn't know how many IOPS we were doing per second. Didn't really know. The only thing we knew is that we were too big in terms of storage. So we chose SQL Server 2012 Standard Edition because we were on a BizSpark license. Eventually, BizSpark is going to expire for us. We didn't want to get stuck with sticker shock when it came time to open up our wallets for that license. Storage allocation, we just took the max. If they're offering 1 terabyte, we'll take 1 terabyte. Storage is cheap. Downtime is not. So we chose 1 terabyte across all of our nodes. IOPS, our busiest database, we partitioned or we provisioned 7,000 IOPS on our busy database, which is that green one that I showed you before. It's kind of the hub of all of our data. None of the shards have any provisioned IOPS. They're not as busy. We've distributed that load. We do see occasional hotspots. We have some celebrities that use our service. When Justin Bieber uploads a video, we see huge traffic spikes and a large number of database queries. Again, changing IOPS or changing any type of storage in SQL Server does require downtime, something we didn't want to do. So we just took 7,000 IOPS on the largest instance. Instance size, busiest instance, which is that green one again. We just took the max M2 4XL. All of our shards use a M2 2XL. Changing instance size, it shouldn't require downtime, but we didn't want to risk it. And then everything is placed in a VPC. VPC guarantees node affinity, but moving across different availability zones does cause some sort of downtime. So how do we design for high availability? We didn't design for fault tolerance. So we can afford a downtime. We can queue messages. We'll guarantee that they'll get there eventually. So we designed for high availability. Amazon RDS and VPCs, at the time that we provisioned, there was no multi-AZ placement groups available, so you have to provision that SQL Server in one particular availability zone. So you do have a single point of failure. So just be aware of that when you are designing to run your SQL Server in RDS. Sharded model. So a user exists in one of 64 consumer shards and one of 64 producer shards. If we lose a shard, only about 1.5% of users are affected. If we lose a database, only 1.5% of users are affected. If we lose an actual instance, we affect about 12.5% of users until we can bring that back online. For eventual consistency, again, we're using SNS and SQS visibility timeout, or message visibility timeout. It gives us the ability to get that database back online without losing that message. And we sharded the SQS queues so that if there's an instance down or there's any sort of backup, it only affects 1/8 of our entire environment. Snapshots. This is kind of what we really like. Set it and forget it. It just works. We've had to use it before. Developers do run updates without where clauses. So it happens. So getting a database back online reliably is very, very important to us. It does take time. 25, 30 minutes is what we typically see to get a database from a snapshot back online. So we bring up that snapshot in a secondary instance, and then we just merge a table that the developer screwed up. It's pretty easy to mitigate that as long as one of the developers gets their hand up and says, oops, I made a mistake early on. It's fairly easy to recover. Also, the snapshots allow us to regularly refresh non-production environments. So if a developer is working on something new in a dev environment, test environment, QA environment, we have automated scripts written in Python using the Bodo library that create snapshots and then restore to those environments. It takes about an hour. We restore to a staging set of servers, and then we just do a name swap. Security considerations. We're a small enough team. We follow the Facebook model. So every developer has access to everything, unrestricted access. It creates less friction. Developers are more efficient. They're able to get they're able to troubleshoot a lot more quickly. But with great privilege comes great responsibility. So you screw something up, you got to break it, or you got to fix it. So some of the other basics, just the kind of does. Application config files use a restricted user account that only has access to update, insert, delete, and select. The databases sit in a private VPC segment. They are not publicly addressable or publicly accessible. We have some port restrictions done, but we do all that restriction at the security group level. We don't use any sort of like natted tables or any sort of IP tables. Developers can connect over VPN. We have an open VPN instance sitting in the public segment of our environment. Developers can work from home, get unrestricted access across any VPC. So we kind of flatten our entire environment to allow developers to connect to production, dev, et cetera, through open VPN. And then support staff, business analysts, anybody that wants to do a select query, business intelligence type of stuff, they get a read-only database account. So we don't have to worry about them, in addition to developers, running an update without a where clause. So that's it. I encourage you guys to check us out, download our application. We have a few other applications in addition to Viddy in the App Store. Try us out, let us know what you think, and I'll use the remaining time for questions.